Hello everyone, and if you're noticing an immediate audio improvement change, that's because I realized that my screen recorder was actually compressing my audio. So now I'm using a professional audio recording software, so hopefully you won't be hearing a bunch of static or weird artifacting in the background. Anyway, this is video 5, and today I'm going to be talking about motion graphs. The first quantity I'm going to be talking about the motion graph of is going to be displacement versus time. So imagine you have a ball held at a fixed distance d away from the point that you are labeling as 0. Now you might be labeling this as 0 for a whole myriad of reasons, but just assume that you're labeling it as 0 for some arbitrary reason. If you were to plot a displacement versus time graph, that is, displacement being in the y-axis and time being in the x-axis, what would this graph look like? Well, considering that this value of displacement is not changing over time, it would actually just be a constant rate, a flat function of value d. This is because if you were to check on this ball at time 0, or at some time later, let's say time equals 100, it would be in the same place regardless of when you were to check the ball. So this makes sense as the ball is at rest, which is where you get this constantly flat line of value d. Now, instead consider the case where this ball is instead moving at velocity v for this time interval. What then would be the displacement versus time graph? Well, if we return to our equation for velocity in terms of displacement in time, where we have the average velocity is equal to delta x divided by delta t, we can solve for delta x in terms of v and delta t. So delta x is equal to average velocity times delta t, which, since velocity is constant, we can actually simplify this to displacement is equal to velocity times time. Because time is our independent variable and displacement is our dependent variable, this actually gives a linear relationship between displacement and time. If you imagine this is y and this is x, you may recognize this from one of your Algebra 1 classes where v, this constant value velocity, is actually going to be the slope of our function. So, writing this in graphical form, we still have our x-axis as t, and our y-axis is displacement, and we're still going to be starting at the same value of d, remember, because this is where it is at time equals 0. But we are now going to protrude outwards at a linear rate of a slope v, where v is our velocity. So the important thing to remember about position versus time graphs is that their slope will give you velocity. Well, how then can we infer our velocity versus time graph from this graph alone? Imagine you were only given this graph and you were asked to provide a velocity versus time graph. Well, looking at our formula for velocity, we find an identical relationship to y equals mx plus b, rise over run, slope, and that is what we just talked about. So how do we find velocity? Well, we use the slope formula, where m is our slope, which is equal to delta y over delta t, or delta x. So what is our rise? Well, our rise is any change in x, or displacement, so delta x, and our run is any change in time, so delta t. So the slope is delta x over delta t, and that is how we would therefore find our velocity versus time graph. We would take the slope of this line at every point along it, and depending on the value of that slope, we would get the value of our velocity versus time graph. So what would this look like? Well, because this is a linear graph, it has a constant slope. Therefore, it should make sense that if we were to draw our velocity versus time graph, so velocity versus time graph, we would get a flat line of value v. Our velocity that we stated existed in the problem statement. And while yes, you could directly infer this from that, I think going through it in the slope way makes more sense in this case. Otherwise, it would be a little bit too straightforward and it wouldn't be as obvious how to do this for problems where you aren't given a constant velocity. Now, from this graph alone, just like in the last example, how do we then infer our position versus time graph? Well, the way we do this is by taking this equation from earlier and interpreting it in a different way. We find that displacement is velocity times delta t, or your time interval. So if we take this entire time to be our time interval, and this value of v to be our velocity, by multiplying the two together at every point, we get our value of displacement. But because our velocity function is flat, we can instead interpret this as finding the area under this rectangle. And in fact, it doesn't matter if our velocity function is flat. By finding the area under our velocity versus time graph, we can then infer our displacement versus time graph. And this is the case for all velocity versus time graphs. And that's what you should remember about velocity versus time graphs. By finding the area under them, you can then infer the displacement versus time graph. Comparing this to our graph for displacement, this makes sense, as if you plot it, small version in the top right corner here. If you remember, this is what we got. If you find the area up to this point, for example, this area right here is going to be small. The area of this rectangle is very small, so it would correspond to a smaller point on this graph. However, if you were to find the total area up to this point, this area will be much larger and would therefore correspond to a higher point on this graph. I hope this has given you some intuition for how to derive position versus time graphs from velocity versus time graphs, and vice versa. As to find this, we would just take the slope. So take the slope of the position versus time graph, we can get back to our velocity versus time graph. However, there's one quantity I still have not talked about, which is, again, very important to physics, which is, you guessed it, acceleration. The thing about acceleration that's important to note is that acceleration has the same relationship with velocity as velocity has to displacement. This means that the relationships that we found between velocity and displacement are the same for acceleration and velocity. This means that the slope of a velocity versus time graph will give you acceleration, and therefore the area under an acceleration versus time graph will give you position. As a final exercise in this, I want to consider the case where we have an object traveling at a constant acceleration, and I want you to see if you can try and find the position versus time graph. Take a minute, think about it. If you can't do it, that's okay, because I'm going to go over it in a second. Pause the video if you need. Now, if you haven't paused the video, or you just wanted to see the solution, let me walk you through it. So, getting rid of these for a moment, I'm going to draw the acceleration versus time graph of constant acceleration. So, acceleration will go on our y-axis and time will go on our x-axis. Because this is constant, this is going to be a flat line of value a. Now, to find the velocity versus time graph using this graph, if you remember, we take the area under this graph here. Because the area under this graph is going to be our value of a times t, we have our velocity versus time graph being t on our x-axis, and this point being a times t, because this is the expression for this function. The value of velocity at any given time is going to be acceleration times time. From this, then, how do we find our position versus time graph? Well, it's not as simple, because rather than finding the area under a rectangular region, we are now being asked to find the area under a triangular region. How do we do this? Well, if you remember from geometry, the area of a triangle is 1/2 base times height. what is the base in this case? Well, the base is just going to be t. And what's going to be the height? Well, the height is going to be our value of velocity at every given point, which we already know is a times t. So times a times t. So this is going to be equal to 1/2 acceleration times time squared. Now, if you take a look at your AP Physics equation sheet, this will be very reminiscent of several formulas that are on there. Formulas which I will go into more detail in the next few videos. Now, moving forward from this, having this formula, what would a position versus time graph look like? Well, if you remember, we still have to start it at our value of d, because that's where we are, time equals 0. This is displacement and this is time. But rather than having a linear relationship with time, we have a parabolic relationship with time. Because t is our independent variable, x will have a parabolic relationship with t because here t is squared. This makes sense because we wouldn't expect the slope to be constant because our value for velocity is constantly changing depending on our value of acceleration. This means that for higher values of acceleration, we should expect faster growing parabolas. And for slower values of acceleration, smaller, we would expect slower growing parabolas because your slope is changing less fast because your value for velocity is not changing as fast. I hope this makes sense, and I know this was a lot to cover today, so if you have any questions, please feel free to let me know. Otherwise, have a great day.